Myself, Pranab Sinha Chaudhary. Today I am going to present hydro generator, mainly part 1. In preface, the conversion of mechanical energy of the turbine into electrical energy is to be made through the electric generator. There are two major components of the generator. One, rotor. The rotor is the rotating assembly on which mechanical torque of the turbine shaft is applied. Number 2, stator. The stator is a stationary component where a voltage is induced by magnetizing or exciting the rotor. In synchronous generator, armature is the stationary part and the field is the rotating part of the machine. For power generating plant, two types of synchronous generators are used. One, salient pole type, is used for low and medium speed application, that is in hydel plant. Two, cylindrical pole type is used for high speed applications, that is thermal plant. The main control mechanism of the generator lies at the exciter regulator, which brings into a specified state and stabilizes the output voltage. The speed of the generator is to be determined by the nature of the turbines as specified, except when geared with a speed variation. In general, for a specified value of power, a decrease in speed will increase the physical size and cost of the generator. Let's have a design criteria. Underneath constraining factors for entertaining large salient pole hydro generators specified for installation up to 1970. 1. Insulation part. Stator and rotor insulation was of class B with organic binding material of lower temperature rises, that is maximum permissible temperature is 130 degree centigrade. 2. Suitable material had to be searched out for rotor rim punching, etc., which was required to limit the rotor diameter so as to permit operation at runway speed. 3. Bearing arrangements. Top thrust and guide bearing supported on heavy brackets capable of supporting total generator weight was provided with a bottom guide bearing to all hydro generators, including slow speed large generator, which constitutes majority of large hydro generators. This resulted in high cost of the machine and structural part. Number 4, the response time of shaft mounted excitation systems were slow and unable to meet the requirement of quick response for large generators feeding to large modern grid systems. Number 5, stability requirements for long distance transmission lines required to feed distant load center oblique grids was achieved by manipulating reactance, excitation, response ratio, and flywheel effect. This resulted in bigger size of the machine. As the grids were small in size and capacity, so there was no stringent requirement for voltage and frequency variation. Number 7, small hydro units were typically installed to feed mainly to remote areas and obviously deployed in isolated mode. For small hydro units, turbines of slow speed were directly coupled to high cost slow speed generators. Hydro stations were manually operated. The loading characteristics was very poor. The small hydro units became highly uneconomical to operate because of low load factors, high installation cost, and very high running cost. Evaluation in design technique. Initiation of the design technique of a large hydroelectric generator requires a specification of performance, usually drawn up by the customer, which contains 1. kVA rating, power factors, line voltage, frequency, number of phases, temperature rise of the winding and core, rated speed, overspeed, and flywheel effect. Out of all critical items used, as the stator frame is of larger diameter, so stator is the largest part in the whole hydro generator and plays an important role with respect to the performance parameters of the entire system. The major components of the stator assembly, which comprises of 1. stator winding, that is bar oblique coil, stator frame and core, stator sole plates. The above mentioned components should have to be designed to withstand prolonged application of the underneath forces. A. Mechanical forces acting on the structure, that is axial, radial, and tangential. B. Unbalanced magnetic pull between rotor and the stator. C. Static load acting on stator frame. The mechanical forces, as mentioned, are transmitted through the stator frame, which is in turn is passed onto the foundation. So these electrical and mechanical parameters for a specific generator output are to be chosen in such a way that the design provides a sufficient amount of strength and stability to the system. Hydraulic turbines driven with large salient pole generators are obviously slow speed machines in the range 80 to 375 RPM with large number of rotor poles. These salient pole hydrogenerators interconnected with large grids have undergone considerable changes in configuration over time, which has resulted in reducing size of the hydrogenerators considerably from the electrical and mechanical point of view. In the present context of the grid power system, the hydro units are subjected to a wide variety of operating conditions. So, specifications are prepared by the customers with the intention of achieving a winding life expectancy of 35 years or more under anticipated operating conditions. Reinforcement in the following areas is most prominent. A. Implementing better insulation for stator and rotor winding, that is to specify class F insulation system for the stator winding and for the rotor winding with class B temperature rise over the ambient. Ambient temperature B, ambient temperature rise has to be determined carefully from the temperature of the cooling system. C, improved version of core material. D, improvised ventilation and cooling system. E, advanced manufacturing technology. F, formation of large grids requires special design consideration for operation and stability. Site operating conditions as per IEC 0054, IEEC 5012 and IS 4722. 1. Maximum ambient temperature steady state duty. Salient pole open ventilated air cooled synchronous generator are so designed to operate successfully when and where the temperature of the cooling air does not exceed 40 degrees centigrade. Salient pole totally enclosed water to air cooled synchronous generators are so designed to operate successfully when and where the secondary coolant temperature at the inlet of machine or heat exchanger would not exceed 25 degrees centigrade. If the cooling air temperature ambient exceeds 40 degrees centigrade or cooling water temperature exceeds 25 degrees centigrade, then maximum allowable temperature based on temperature rise on reference temperature 40 degrees centigrade and 25 degrees centigrade of the insulation class is specified instead of temperature. The minimum temperature of the air at the operating site is minus 15 degrees centigrade. Then the machine being installed and in operation or at rest has to be de-energized. If site operating conditions are deviating from these values, then the OEM, that is original equipment manufacturer, should be informed of actual site conditions. Second part is the altitude. Location, height above the sea level not exceeding 1000 meters. For machines intended for operation on a site where the altitude is in excess of 1000 meters should be specifically brought out according to the OEM. Number of stars and application of load. This is the number 3. Anticipated number of starts and maximum MVA power and reactive power loading with rate of change are to be specified to the manufacturer to take into account in the machine design. The method of starting must be identified in the case of picking stations. For voltage and frequency limits for generators as per IEC 60034, generators should be thermally capable of continuous operation within the capability of their reactive capability curves over the ranges of plus minus 5% in voltage and plus minus 2% in frequency. In the chart, voltage limit plus minus 5%, that is normal. But in the emergency case, that is to be plus minus 5% to plus minus 8%. Frequency limit in normal case plus minus 2%, but in emergency time or emergency cases, plus 2% to plus 3%, minus 2% to minus 5%. Any shifting of rated values of voltage and frequency, then temperature of generator components may progressively increase. Generators will also be capable of operation within the confinement zone of their reactive capability curves within the range of plus 3% to minus 5% in frequency, which further reduction of insulation life as due to effect of sudden rise of temperature and temperature differentials. So, operation beyond normal limit should be restricted in extent, duration, and frequency of occurrence. Stability and excitation margins. That's the fifth one. And it's a very important one because the excitation control features are the most decisive factor for more flexible means of operating the synchronous machine with the optimal reactive power flow according to the network conditions. The armature winding is commonly placed in the stator and field winding is placed in the rotor. The Salient pole generators have a large number of poles and lower operating speed and suitably applicable for hydropower plant generator. The term salient means projecting. A salient pole consists of poles that are projected out from the surface of the rotor core. The rotor is subjected to changing magnetic fields. That is why it is made of steel laminations to reduce the eddy current losses. After the field coil is placed around each pole body, these poles are fitted by a dovetail joint to a steel spider keyed to the shaft. Salient pole rotors have faces to damp out the rotor oscillations during a sudden variation of load conditions. A non-uniform air gap accompanies a salient pole synchronous machine. Air gap is minimum under the pole centers and maximum between the poles. Next. The pole faces are so shaped that the radial air gap length increases from the pole center to the pole tips so that flux distribution in the air gap is sinusoidal. This will help the machine to generate sinusoidal electromotive force, that is EMF. The rotor is excited through the field winding with a DC power source. The end of the field windings is connected to a DC winding by the brushes on the slip rings. The prime mover, when makes to rotate the excited rotor, an electromotive force is generated to the stator winding, whose magnitude and frequency correspond to the excitation power in the rotor and the rotating speed of the prime mover. To give the alternate north and south polarities, the individual field pole windings are connected in series. Under normal operating conditions, the rotating field in the stator and rotating rotor remain in synchronism. When the generator is connected in parallel to the system network, excitation control has met to change only the reactive power output of the generator. An increase of the excitation current makes the generator to produce more inductive reactive power, thus compensating the inductive load. A decrease in excitation current ultimately leads to a situation where the generator starts to absorb inductive reactive power from the network. This situation is referred to as under excitation and is not a normal operation mode of the generator. Next. As the generator is electrically coupled to the network, the rotation speed of the generator would not be increased by any increase in torque of the prime mover. Instead, it increases the active power output of the generator. If the prime mover torque is decreased below the level of rotating speed of the generator due to matching of the system frequency, the generator starts to work as a motor trying to rotate the prime mover with the synchronous speed. This situation is referred to as reverse power operation. The reverse power operation is harmful to the generator and also to the prime mover. Thus, the situation has to be recognized by the protection release. The figure shows an example of synchronous generators' capabilities and constructional limitations for operation under different conditions. A normal operation is carried out in overexcited condition, injecting reactive and active power to the network. When a synchronous generator is started, it is speeded up with the prime mover close to the network frequency, and the excitation current is applied to reach the nominal terminal voltage. It is the synchronous generator capability curve. One is under-excited operation, other is normal overexcited operation. Next. Capability curve of the synchronous generator. Capability curve of a synchronous generator demarcates the boundaries within which the machine can operate safely and can deliver reactive power continuously without overheating. The Q, that is MVAR, reactive power, is controlled in the generator by controlling the excitation field current, IF, and the P, that is the power in megawatt, is controlled by a prime mover. A synchronous generator has a field winding on a rotor which needs a DC excitation current. The change in excitation current results in a change of reactive power and a change in the generator terminal voltage. Generator rating is specified in terms of MVA and power factor at a particular terminal voltage. Active power delivered by a generator is only limited by the power delivering capability of the prime mover, that is turbine. But the reactive power, which a generator can deliver continuously without overheating, is governed by three limiting factors. One, armature current limit. Second, field current limit. And third one, end part heating limit. Armature current limit. Armature current, I, is the load current in the stator winding. The current will lead to heating of stator winding due to ohmic loss, that is I square R, where R is the resistance of the stator winding. During operation of the generator, such phenomena needs to balance between the heat produced by I square R loss and cooling of the stator winding. If the heating of stator winding is more than its design cooling effect, then it will lead to excessive heating and consequent damage to armature of generator. Therefore, armature current of generator shall not exceed the design maximum value. Let us now plot this armature current limit on PQ plane. As we know that complex power is given as P plus J Q is equal to VI, where I is conjugate of, that is I star is conjugate of I, is equal to VI cos phi plus J sin phi. Taking modulus to both sides, we get P square plus Q square is equal to VI square, which is an equation of circle with center at origin and of radius VI as shown in figure. Circle represents the armature current heating limit on generator operation. Generator shall always be operated under the circle to avoid overheating. Field current limit. Second point. A maximum limit on the value of field current IF is imposed by the heating in the field winding due to IF square R loss, where R is the resistance of the field winding. It indicates that generator can only supply absorb a fixed maximum value of the reactive power. We know E is equal to Vt plus Jix x s, where E is no load excitation voltage, Vt is terminal voltage, I is load current, and Xs is synchronous impedance of generator. The above equation can be represented by the phasor as shown below. From the phasor diagram, Xs I cos phi is equal to E sin phi. Now we see the equations as prescribed in my slide. You go through, assuring the generator terminal voltage Vt and the synchronous impedance Xs to be constant. The variable in the above equation is only E. Air gap flux is directly proportional to the field current IF. Hence, this equation represents the locus of field current. From the equation 5 is the is the equation of a circle having center at 0 minus Vt square by xs and radius EVT by xs. This circle is shown below. The above circle represents the field heating limit. Generator must be operated within this circle to avoid field heating. End part heating. Number 3. End part heating is rather localized heating at the end region of the stator core of generator. Such type of localized heating is a basic result of eddy current loss in laminations of stator core due to end turn flux of armature winding. This heating phenomena imposes an operational limitation of synchronous generator, which is known as end part heating limit. Basically, the laminations of stator core are so stacked that air gap magnetic flux lines are parallel to the laminations. This criteria has fulfilled to reduce flux linking by the laminations and hence reduces the eddy current loss. But the internal leakage flux of armature enters and leaves the stator core perpendicularly as shown in figure below. This causes higher leakage flux since phi is equal to BA by the stator core laminations, which subsequently induces eddy current. This eddy current produces I square R loss and leads to heating of end part. Now see the diagram. End part heating in synchronous generator. When generator is in overexcited condition, the retaining ring of the rotor has become saturated, which offers high reluctance path to the leakage flux. Therefore, the follow of leakage flux to the stator reduces, and hence possibility of the end part heating has also become in the lower side. But when generator is in underexcited condition, the retaining ring of the rotor is in unsaturated condition. Hence, retaining ring of the rotor offers low reluctance path to the leakage flux. Also during underexcited condition, the flux produced by the armature current adds to the flux produced by the field current. Therefore, end turn flux enhances the flux axial in the end region. This results more heating in end part of the stator, and the load has to be cut down for safe operation of the generator. Thus, end point heating imposes a limit on generator reactive power when machine is operating under leading power factor condition. Leading power factor means the machine is underexcited, therefore field current will increase to meet the required working flux. This will cause more end flux in the machine, which will link with the stator core lamination to cause eddy current heating. Having sum up the three constraints to get the capability curve of the generator, which is shown in the next slide. This is the underexcited condition, an overexcited condition power factor. From the capability curve, armature heating and field heating limit are shown by the curve QR and QT respectively. Both these curves cut at point Q, which means the generator shall be operated at this point under lagging power factor condition. End part heating is shown by the curve RS for leading power factor condition, armature heating limit curve, and end end part heating limit curve cut each other at point R. This point is the point of operation of generator under leading power factor condition. Generator operation shall always be confined within the capability curve, else it may damage its insulation due to overheating. Capability curve is supplied by the OEM and will be guideline for operating the generator. Capability curve is all about heating of different parts. If the cooling system is somehow enhanced, then the limits of generator operation will also increase. This means the individual limits will increase and the operation boundary will be broadened. As per IEC 6054, the points to be noted that during operation, if there is any occurrence of deviation from rated values of voltage and frequency, then respective temperature of the components may progressively varies. Underneath effects of for variation from rated voltage and frequency, a continuous operation at output close to the limits of the generator's reactive capability curve may cause insulation to age thermally at approximately 2 to 6 times of the normal rate. B. Generator will also capable of operation within the confined zone of its reactive capability curve and obviously within the ranges of plus 3% to minus 5% in frequency and further reduction of insulation life. To diminish the reduction of the generator's lifetime due to the effect of the sudden rise of temperature or temperature differentials, any operation deviating from the rated voltage and frequency limits as prescribed should be cut down in extent, duration, and frequency of occurrence. The generator output would have to be cut down or other preventive measures should have to be taken as soon as practicable. The boundaries as defined by the generator's reactive capability curve should have the result in the magnetic circuit of the generator to be overfluxed or underfluxed by no more than 5%. If the operating frequency deviates from the rated frequency, which ultimately affects the equipment other than the generator, for example, the turbine manufacturer will specify the ranges of frequency and corresponding periods during which the turbine can operate and the ability of the auxiliary equipment to operate over a range of voltage and frequency should also be taken into consideration. Transient emergency duty requirements. A generator complying of these guidelines will be suitable for withstanding exposure to transient event and emergency duty exposed on generator because of any power system fault, sudden short circuit at the generator terminals. A generator should be capable of withstanding without injury for a period of 30 seconds if there will be three-phase short circuit at its terminals when operating at rated MVA and power factor and at 5% over voltage with fixed excitation. The machine shall also be capable of withstanding without injury any other short circuit at its terminals of 30 seconds duration or less in accordance with the IEEE C50 122005. Generator circuit breaker needs to be selected accordingly. Let's stop here. Further to be continued at later stage. Last but not the least, to have a request that please get ahead with the topic to like, share, and subscribe. Thanks.